Welcome to Mickey Study Circle channel. In this video, we shall see how to perform the stress analysis of a tapered bar subjected to an axial load. So before we start with the problem statement, let us try to understand the concept of a tapered bar. So basically, a tapered bar is a cylindrical bar which is having two varying diameters. So as you can see here, it is having a bigger diameter at one end and a smaller diameter at the other end. And both the diameters or the circumferences of the circles are connected by the slant lines. So you can just see that in the front view, it appears as if it is a trapezoid. So this is the bigger end and this is the smaller end. And we will just move on to the problem statement now. So we can just see that we have got a tapered bar of diameters 40 that is the bigger end diameter, and 20 of smaller diameter. And the section is ABC. So AB is the straight portion of the bar, and BC is the tapered portion of the bar. So the straight portion of the bar is having a length of 1000 and the tapered portion is having a length of 500 So moving on to the problem statement. So we have a 1.5 meter long steel bar which is having a uniform diameter of 40 for a length of 1 meters, and in the next zero point 0.5 meter its diameter gradually reduces to 20 from 40 as shown in the figure. So we need to determine the elongation in the bar, the stress and also the reaction forces when subjected to a tensile load of 160 kilonewtons. So we can assume the Young's modulus of the material of the bar to be equal to 200 GPa and the Poisson's ratio to be equal to zero point 0.3. So before we start with the simulation using the ANSYS APDL, let us try to compute the values using the strength of material approach so that we can compare the answers. Firstly, let us proceed with the calculation of the reaction force. So writing the free body diagram, we can just see that a reaction force is a force which is opposite to the applied force. So the force Fx is the tensile force which is acting away from the origin. So the reaction force will be towards the direction opposite of the applied force. So considering the summation of all the forces in the direction x to be equal to 0, we have got the sum of Rx and Fx to be equal to 0. However, we do know the magnitude of Fx which is equal to 160 kilonewtons. So therefore, upon substitution, we get the reaction force magnitude to be equal to minus 160 kilonewtons. So this is the value of the reaction force at the support. Next, let us try to compute the value of the deformation. So, as we can see in the problem statement, the bar is composed of two parts. One is the linear or the straight part, and the other one is the tapered cross-sectional part. So, since the area is to be considered by calculating the diameter of the circle because it is a circular bar, we can use the formula of A is equal to pi by 4 d square in order to compute the area of cross section of the straight portion of the bar. So the magnitude of load acting is 160 kilonewton, which is common for both the linear as well as the tapered portion. So this is the area of cross section of the linear portion of the bar, and this is the Young's modulus of the material of the bar. So substituting the values, we get the delta L to be equal to 0.636 for the straight portion of the bar. So now let us compute the deformation in the tapered cross section of the bar. So we do have a mathematical model for the tapered cross section, that is 4 into P into L by pi into E into D1 and D2, where D1 and D2 are the bigger end diameter and the smaller end diameter respectively. So we do know the values of the load, that is P, and the length of the tapered portion of the bar, which is equal to 500 or zero point 0.5 meters, and the diameters being 40 that is the bigger end, and the smaller end diameter being 20 and the value of E being 200 GPa or 200 megapascals. So upon substitution, we do get the elongation in the tapered section of the bar to be equal to 0.6366 So upon addition of both the elongation of the linear cross section as well as the tapered cross section of the bar, we get the total elongation to be equal to 1.2732 So this is the total elongation of the bar when it is subjected to a tensile load of 160 kilonewtons as shown in the problem statement. Next, let us end by computing the value of the stress. So the stress in the linear portion of the bar, that is AB, is computed by the mathematical model, which is nothing but the ratio of the load acting over the given cross-sectional area. So again, the cross-sectional area is computed by using the mathematical model of the area of the circle, that is pi by 4 d square. So we do get the magnitude of the stress to be equal to 127.32 megapascals, which is nothing but the tensile stress. Next is the stress in the tapered section, which is given by the mathematical model P by pi by 4 into d1 minus of k into x square. So where k is nothing but the difference in the bigger end and the smaller end over the length of the tapered section. So x is equal to 250 mm. Upon substituting and solving, we do get the value of the sigma to be equal to 226.35 MPa, that is 226.35 megapascals. So now let us compute the values of the reaction force, the deformation, and also the stress using the ANSYS APDL software. So now let us begin the simulation. First, by going to the file menu and selecting change title. So let us enter the title as stress analysis of a tapered bar and click OK. So just right click in the screen and tell replot. So you can just see that the title of the experiment or the analysis part is being produced here. That is the stress analysis of the tapered bar. Now let us go for preferences. Select the domain which is structural. Click OK. Go for preprocessor. Select the element type. And here we are going to just deviate by selecting a beam element because the cross-sectional area is circular in nature. So we'll select beam and the element is 3D finite strain element. Click OK. So you can just see that the 3D finite strain element is also called as beam 188 in the ANSYS library. So instead of link 180, we are selecting an element called as beam 188. So click close. And now let us go for assigning the material properties. So go for material props and select material models. And material model number one, structural, linear, elastic, isotropic. So feed the values of the Young's modulus, which is 200 E5, and the Poisson's ratio, which is zero point 0.3. Click OK. Since it is assumed to be a uniform composition of the material, we are going to just assign a single value here. So now let us define the geometrical parameters. So let us select sections and select the element as beam and then go for common sections. And in the common section, let us just name the first section as the big end. And since it is having a circular cross section, in the subtype select a solid circle. So this represents the hollow circle. We are going to select it as a solid circle. So let us assign, you can just see that the R is representing the radii. So the radii of the bigger end is 20 mm because the diameter is 40. So just click OK. And now again select common section. Change the ID from 1 to 2 and then name this as small end and select the subtype to be equal to circle and the radii of the smaller end to be equal to 10 mm because the diameter is 20. So click OK. So now we have defined the bigger end and the smaller end diameters. Now let us go for taper sections and select by XYZ location. So this taper section ID is given by the number 3 and you can just name the section as tapered part or just the taper bar. So you can just select the location of the beginning of the bigger end. So it is going to begin at the end of the 1000 um, or 1 meter and the small end is at 1500 so just enter the parameters. So the ending section of the tapered portion and the beginning section of the tapered portion, that is 1000 and 1500 as given in the figure of the problem statement. So click OK. So now we have defined three parameters. One is the bigger end, the smaller end, and also the tapered cross section by using the XYZ location. So the geometrical properties have been fed, and now it is time for us to create the model. So let us create the FE model by using the nodes. So go for modeling, select create, and select nodes, and in active coordinate system. So the first coordinate or the first node is always the origin. So enter one and click apply. So 0 is taken by default. And the next node is node number 2, which is at a distance of 1000 mm from the origin. That is the beginning of the tapered section. So click apply, and next on the final node is now node number 3, which is nothing but the end of the tapered section at a distance of 1500 mm from the origin. That is 0 to 1000, 1000 plus 500, which is 1500. So click OK. So now we have got three nodes in the active coordinate system. In element attributes, select the element type number as beam 188 because that is the only element that we have picked from the ANSYS library. And the material number is just 1 because it is the single uniform composition of the material throughout the bar. And now you can just enter the target element shape to be straight line. So just select straight line and click OK, and then go for auto numbered and select through nodes, pick node number 1 and node number 2 and click OK. Now again go for element attributes, select the straight line, select the taper section and click OK, and then go for auto numbered through nodes and select 2 and 3, that is the tapered section. So this is the tapered section of the bar. So now let us go for application of the boundary conditions, that is the constraints and also the load. So go for loads, select define loads, click apply, select structural displacement on nodes because we have created the geometry using the nodes. So select node 1 and click OK. Select all degrees of freedom and enter the degrees of freedom to be 0. Click OK. So since it is a beam element, you can just see that the constraint for the displacement is fixed by this particular symbol here. So now let us feed the value of the force using the command prompt. So let us type the syntax. So F indicating the force, and the node is number 3, and the direction of the application of the load is Fx, and next is the magnitude of the load, which is 160 kilonewton. So let me feed the values in newtons. So 160 followed by three zeros. So this is 160 followed by three zeros in newtons. So now you can just see that at node number 3 the load is uh, acting. So now let us go for computing the solution. So just go for solution and select solve the current ls, that is the load step. Click OK, and you can just see that solution is done, is appearing. Click close. So now it is time for us to extract the results. So go for general post processor and select list results and select reaction solutions, all items, and click OK. So you can just see that at node 1 where the support is there is a reaction force which is equal to the magnitude of the tensile load acting on it, but with a negative sign. So it is compressive in nature. So that is minus of 0.16 followed by 6 zeros, which is nothing but 160 kilonewtons. So close after recording the values of the reaction solution. Now let us compute the values of the displacement. So go for nodal solution, select DOF solution, and select the displacement vector sum and click OK, and you get the displacements at node 2 and 3. So at node 1 we have already defined the displacement to be 0, so you can just see that at x, y and z direction the displacement is 0. At node 2 this is the displacement, that is at this portion of the bar, that is 0.63712. You can just compare the values of the elongation that we calculated using the strength of material approach for the section AB of the bar, and next for the section BC it is equal to 0.12034. So this is the values of the deformation or the elongation in the bar for element 1 and element 2. So close this after recording the values. Now let us enter SAT in the command prompt and press enter. So this is the syntax that is used for defining the stress component from the library. Go for element table, select define table, click add. So we'll select by sequence number, LS, that is the linear stress, enter 1. So 1 indicates the number given for the beam 188 element to compute the values of the linear stress in the ANSYS library. So click OK. So you get to see the label as LS1, click close. Now let us compute the values of the stress. So go for plot results, select contour plot, select element table, and by default LS1 is selected. Select S average, click OK, and you get the values of the stress. So the minimum stress is 127.423 megapascals and the maximum stress is 226.53 megapascals. So if you want to have a 3D view of the object, go for plot controls, select style, size and shape, and switch on the display of the element. Click OK. So let us go for nodal solution. Select DOF solution, displacement vector sum, click OK. So you get to see the 3D view of the object. So right click and select isometric. So you can just see the distribution of the deformation through the bar. So this is the values of the maximum displacement or the elongation. So from the bar, you can just see at every direction how the distribution of the deformation is represented. So if you want to just see the animation of this, go for plot controls, select animate and select the deformed shape and select deform plus undeformed, click OK. So you get to see the animation like how the bar is getting elongated. So this is the actual length and this is the elongation that is going to happen due to the application of a load of 160 kilonewtons. So to end the animation, just click close. So now in order to compute the multiple results in a single window, go for plot controls, select multi-plot uh, controls. So before that, select multi-window layout, select two, that is top and bottom. So it is going to divide the window like this. Now go for plot controls, select multi-plot controls. In window 1, in the entity plots, select OK, select deformed shape and click OK. So select deformed plus undeformed and click OK. So right click until replot. So you get the values of the deformation in the window 1. Similarly, let us have the stress distribution in the window 2. So go for multi-plot controls, select window 2, entity plots, click OK. Go for element solution, click OK. Select stress and X direction, deform plus undeformed, click OK. So right click until replot. So you get to see the distribution of the stress. So go for view and select isometric. So you get to see the distribution of the stress within the element. So window 1 is detailing us about the elongation and window 2 is detailing us about the deformation as well as the stress distribution within the tapered bar. So in order to save the screenshot of this in the white background, go for plot controls, select write meta file, invert white or black, and you can just save this as tapered bar. So it is being saved as a meta file. Click save. So now let us just go open the file which has been saved. So this is the file. So you get to see the screenshot has been saved in the white background. So just click on file and select save as a JPEG picture or a PNG picture. I'll go with PNG and click save. So a PNG copy of the file is being saved. So with this, we end the stress analysis of the tapered bar subjected to a tensile load of 160 kilonewtons. So basically here, the problem statement is in such a way that the bar is having a uniform cross section over a certain length and then it is getting a tapered cross section over the next part of its length. So this is the stress analysis and the distribution of the stress within the tapered bar. Thank you all for watching.